6 seconds. That's all Soviet radar operators could track it. 6 seconds before the ghost vanished. But in those 6 seconds, they glimpsed something that would change warfare forever. The men watching those screens weren't amateurs. They were elite professionals who had spent years mastering their craft. Learning to identify every aircraft in the Western arsenal by radar signature alone, they could distinguish a Boeing 747 from a military transport at hundreds of kilometers. They knew the precise radar cross-section of every American fighter, every bomber, every reconnaissance aircraft that had ever challenged Soviet airspace. But this was different. This defied everything they knew about physics, radar technology, and the fundamental principles of aerial detection, and it was driving them to despair. This is the story of how a Soviet physicist ignored research became America's most secret weapon, how engineers built an aircraft that shouldn't fly, and how the phrase "we tracked it for 6 seconds" became a symbol of technological revolution. The story begins not in the skies, but in a Moscow technical library in the mid-1960s. There, a brilliant Soviet physicist named Pyotr Ufimtsev was working on seemingly impractical theoretical research into how electromagnetic waves behave when encountering various geometric shapes. His paper, Method of Edge Waves in the Physical Theory of Diffraction, was dense, mathematical, and to most observers, utterly useless. The Soviet military reviewed Ufimtsev's work and concluded that while intellectually interesting, it had no practical military application. They allowed publication, never imagining this decision would haunt them in ways they couldn't foresee. Across the ocean, engineers at Lockheed's Advanced Development Projects Division, the legendary Skunk Works, were desperately searching for answers. American military leaders faced a growing problem. Soviet air defenses were becoming lethally effective. The surface-to-air missile that shot down Gary Powers' U-2 in 1960 proved that flying higher wasn't enough. The Vietnam War reinforced this with brutal clarity. American pilots were being shot down in alarming numbers by Soviet-supplied SAMs. Sleek, powerful fighters representing the pinnacle of aerospace engineering were being swatted from the sky by radar-guided weapons. Something fundamental had to change. In 1974, Lockheed mathematician Denis Overholzer stumbled upon a translated copy of Ufimtsev's paper. As he worked through the dense formulations, he began to realize the Soviet physicist had inadvertently provided a roadmap for what the Americans desperately sought. A way to make aircraft virtually invisible to radar. The insight was deceptively simple. Think of radar like a flashlight in a dark room. A normal aircraft acts like a mirror, the light bounces straight back to you. But what if you could design an aircraft like a carefully angled prism, scattering light everywhere except back to the flashlight? That's what Ufimtsev's equations revealed. Invisibility through deflection, not absorption. Radar works by sending electromagnetic waves that bounce off objects and return to the receiver. The size and shape of the return signal, the radar cross-section, determines visibility. A large bomber might appear as big as a building, while a fighter jet registers like a truck. Ufimtsev's mathematics showed that by carefully angling flat surfaces, you could deflect radar waves away from receivers rather than back toward them. Overholzer quickly wrote a computer program called Echo 1 to calculate radar cross-sections of geometric configurations. The results were astonishing. Using flat-angled panels instead of curved surfaces could reduce an aircraft's radar signature by orders of magnitude, potentially making a fighter jet appear no larger than a small bird. The Skunk Works team, led by the legendary Ben Rich, immediately recognized the revolutionary potential. But translating theory into flying aircraft would prove one of aviation's greatest engineering challenges. Everything aeronautical engineers knew about designing efficient, flyable aircraft worked against radar deflection principles. Curved surfaces that allowed smooth airflow were exactly the shapes that reflected radar most effectively. The angles and facets required for stealth created aerodynamic nightmares that seemed to make stable flight impossible. Early designs looked less like aircraft and more like flying diamonds or crystalline structures. The engineers called their first proof-of-concept design Have Blue. When they showed drawings to experienced test pilots, the reaction was disbelief. This thing couldn't possibly fly. It violated every principle of conventional aircraft design. But the Skunk Works wasn't working with conventional constraints. They were pioneering computerized flight control that would make the seemingly impossible possible. The key was fly-by-wire systems' computerized mechanisms, making thousands of corrections per second to keep an inherently unstable aircraft in stable flight. The first Have Blue prototype took to the skies in December 1977 from Groom Lake, Nevada, remote facility that would become famous as Area 51. The aircraft looked like nothing that had ever flown. Its angular, faceted surfaces gave it an alien appearance that seemed to belong in science fiction rather than on a military airfield. Test pilot Bill Park carefully lifted the strange craft into Nevada sky, his hand ready to trigger the ejection system at the first sign of uncontrollable tumble that many engineers still feared inevitable. But the fly-by-wire system performed flawlessly, making continuous adjustments that kept the ungainly aircraft stable and controllable. More importantly, radar testing produced results exceeding even optimistic predictions. When Have Blue flew against radar systems, the return signal was so small that operators initially thought their equipment had malfunctioned. This flying geometric sculpture had a radar cross-section smaller than a ball bearing. Have Blue's success led immediately to development of a full-scale operational stealth aircraft, designated the F-117 Nighthawk. The program was classified at the highest possible levels. The aircraft was developed, built, and initially deployed in complete secrecy. Even most of the Air Force didn't know the F-117 existed. Pilots selected to fly this revolutionary aircraft were hand-picked from the most elite squadrons. They underwent psychological evaluations to ensure they could handle the immense pressure of flying aircraft that didn't officially exist. They were sworn to secrecy so absolute they couldn't even tell their families what they did. These pilots trained at night, flying only when darkness provided additional concealment. Aircraft were kept in specially constructed hangars during daylight, hidden from Soviet reconnaissance satellites constantly sweeping over American installations. Ground crews worked under strict light discipline, using only red lights invisible to overhead observation. Colonel Viktor Petrova, composite of the Soviet radar operators who faced this challenge, had tracked American aircraft for 15 years. The SR-71, the U-2, he knew them all. He took pride in his ability to identify aircraft types by their signatures, speed profiles, and flight characteristics. But starting in the mid-1980s, something changed. Reports filtered in from radar installations along the Soviet periphery. Operators detected brief, inexplicable signals that appeared and disappeared before proper tracking. At first, these reports were dismissed as equipment malfunctions or atmospheric anomalies. Radar systems, despite their sophistication, occasionally produced false returns. Solar activity, unusual weather, and electronic interference could create phantom signals that experienced operators learned to ignore. But the reports kept coming, sharing disturbing similarities. Signals always appeared in the same areas along logical flight paths for American reconnaissance. They lasted just seconds before vanishing completely. They occurred when American military activity was elevated. A team of Soviet radar specialists assembled to investigate. They reviewed hundreds of radar tapes, searching for patterns. What they found deepened the mystery. The signals, when captured, showed characteristics unlike any known aircraft. The radar cross-section was impossibly small, equivalent to a large bird, rather than a military aircraft. But speed and altitude were clearly those of a high-performance jet. The physics didn't match any aircraft in Soviet or Western inventory. The investigation team considered several possibilities. Perhaps the Americans had developed electronic countermeasures to reduce radar returns. But the signals weren't being jammed or distorted. They were simply extraordinarily weak, as if targets were absorbing or deflecting radar energy. Another theory suggested unmanned drones with unusually small signatures. But flight profiles were too sophisticated, too adaptive to be anything but piloted aircraft. Whatever created these phantom signals was flown by highly skilled aviators who knew exactly how to exploit gaps in Soviet radar coverage. The most troubling aspect was the psychological effect on operators themselves. These professionals had built careers on detecting and tracking any aircraft. Now they confronted something that appeared and disappeared at will, mocking their training and expertise. "We tracked it for 6 seconds." That phrase became dark humor among Soviet air defense personnel, bitter acknowledgment that something fundamental had changed in the balance of power. 6 seconds was long enough to know something was there, but not long enough to do anything about it. The Soviet military hierarchy divided on response. Some insisted reports must be exaggerated. No aircraft could truly be invisible to radar. Others argued evidence was unmistakable and demanded crash programs for countermeasures. The debate was hampered because nobody knew exactly what they were countering. Meanwhile, the F-117 program matured rapidly. By 1983, the aircraft was declared operational, though its existence remained completely classified. Pilots of the 4,450th Tactical Group, later redesignated as the 37th Tactical Fighter Wing, flew regular missions, testing capabilities and refining tactics. These missions revealed both strengths and limitations of stealth technology. The F-117 wasn't truly invisible to radar. Under certain conditions, certain angles, it could still be detected. But its radar cross-section was so small that detection was extremely difficult and tracking nearly impossible. Pilots learned to exploit this advantage fully. They studied Soviet radar deployments, memorizing locations and capabilities of every known installation. They planned routes to minimize exposure to dangerous systems while exploiting gaps and blind spots in coverage. The aircraft's angular design created specific zones where radar returns were slightly higher. Pilots called these hotspots, learning to time maneuvers, so these moments of increased visibility occurred when furthest from radar installations or when terrain provided additional masking. Night operations became standard for F-117 missions. The aircraft's black radar-absorbent coating made it nearly impossible to see visually after dark. Adding another layer beyond electronic stealth, pilots wore specially designed helmets with forward-looking infrared displays allowing them to navigate and target with precision despite complete darkness. Psychological preparation for F-117 missions was as important as technical training. Pilots had to accept flying deep into enemy territory with no friendly aircraft nearby, so no radar coverage to warn of threats, and no possibility of rescue if something went wrong. They had to trust completely in the aircraft's ability to keep them hidden. Unlike conventional fighter pilots who rely on speed, maneuverability, and situational awareness, F-117 pilots embraced deliberate vulnerability. They flew slowly compared to other tactical aircraft. They couldn't engage in dogfights. Their only defense was invisibility. The first real-world test came during Operation Just Cause the American invasion of Panama in December 1989. 2 F-117s struck targets in support of the operation, marking the aircraft's combat debut. The results were mixed in terms of bombing accuracy. One aircraft successfully hit near a Panamanian Defense Force barracks, while the other missed due to pilot disorientation. But the mission demonstrated something far more important. The Panamanian air defense system, equipped with Soviet-supplied radars, completely failed to detect the approaching aircraft. The F-117s flew through defended airspace like ghosts, arriving over targets without warning. For military planners on both sides of the still ongoing Cold War, this was a watershed moment. The implications for potential European conflict were staggering. Soviet military analysts studied the Panama operation intensively, gathering every scrap of information about the mysterious aircraft that had appeared publicly just months before the invasion. Satellite photographs of the strange angular jets confirmed what Western media called the stealth fighter, but actual capabilities remained uncertain. Panama suggested those capabilities were every bit as formidable as the most alarming estimates predicted. If Americans could fly undetected through Central American airspace, they could presumably do the same against far more sophisticated opponents. The Soviet response was a massive effort to develop detection methods countering stealth technology. Research programs explored alternative radar frequencies, passive detection systems, and sensor fusion techniques that might reveal what conventional radar couldn't see. Soviet scientists theorized that while stealth aircraft were designed to defeat high-frequency radars in X-band and Q-band ranges typically used for fire control, they might remain vulnerable to lower-frequency systems. Physics of radar cross-section reduction worked differently at longer wavelengths and aircraft optimized. For one frequency range might still be visible at others. This led to renewed interest in older technologies considered obsolete. The massive over-the-horizon radars built to detect ballistic missile launches operated at much longer wavelengths than tactical radars. Theoretically, these might detect stealth aircraft, though with far less precision than needed for weapons targeting. Another approach focused on passive detection, not relying on radar at all, Infrared sensors could potentially detect heat signatures from jet engines. Acoustic sensors might pick up aircraft sound at certain altitudes. The challenge was integrating these diverse methods into a coherent system that could track targets and guide weapons. The most promising Soviet counter-stealth technology was multi-static radar systems. Traditional radar used a single transmitter and receiver at the same point. Multi-static systems separated transmitter and receiver, positioning them at different locations. This could potentially detect stealth aircraft by picking up deflected radar energy rather than absorbed energy. The theory was sound, but practical implementation proved enormously difficult. Coordinating multiple transmitters and receivers, synchronizing timing with sufficient precision, and processing resulting data fast enough for air defense was beyond Soviet technology in the late 1980s. As the Cold War drew to a close, Soviet military planners faced dispiriting reality. Despite intensive efforts, they hadn't developed reliable methods for detecting and tracking stealth aircraft. The massive air defense network that had been the pride of Soviet military power was potentially vulnerable to American aircraft that could strike with impunity. Then came the Gulf War of 1991. January 17, 1991, 2:38 a.m. Baghdad time. Iraqi radar operators watched their screens with tired eyes. Another quiet night. Then the bombs started falling. They never saw it coming. On the first night of the air campaign, F-117s led the assault on Iraqi air defenses, striking with precision that stunned military observers worldwide. The Iraqi integrated air defense system was one of the most extensive and modern in the world outside the Soviet Union itself. It incorporated Soviet-supplied radars, surface-to-air missiles, and command and control systems representing state-of-the-art air defense technology. Western military planners had expected significant casualties attacking this network. Instead, F-117s flew through Iraqi airspace essentially unopposed. The stealth fighters struck key radar installations, command bunkers, and communications nodes with precision-guided munitions, systematically dismantling the air defense network from within. Iraqi radar operators reported the same baffling experience their Soviet counterparts had described. Targets appeared on screens for mere seconds before vanishing, never long enough to achieve weapons lock. The psychological impact on Iraqi air defenders was devastating. Men trained to trust their equipment and procedures confronted an enemy they couldn't see, couldn't track, and couldn't fight. Some simply abandoned posts, convinced resistance was futile against such advanced technology. Over the Gulf War, F-117s flew approximately 1,300 combat sorties without a single loss. They struck the most heavily defended targets in Iraq, including installations in downtown Baghdad protected by multiple overlapping air defense systems. The aircraft performed exactly as designers promised, achieving tactical surprise on nearly every mission. For Soviet military observers monitoring the conflict, the Gulf War was a sobering lesson. The Iraqis had been equipped with Soviet weapons and trained in Soviet doctrine. Their defeat wasn't just Iraq's failure, it demonstrated the vulnerability of Soviet military technology to American stealth capabilities. We tracked it for 6 seconds. Those 6 seconds told the complete story. The Russian military that inherited the Soviet arsenal after 1991 continued efforts to develop counter-stealth technologies. Research programs initiated in the late Soviet period were maintained, though with reduced funding as Russia struggled through post-Cold War economic crises. One result was development of new radar systems specifically designed to detect stealth aircraft. Russians claimed systems like the Nebo series and later the S-400 air defense system incorporated as features that could detect and track low observable targets. Western analysts debated these claims, but the mere possibility represented significant evolution from the complete helplessness of the Cold War era. The fundamental physics of stealth technology meant detection would always be possible under certain conditions. No aircraft could be truly invisible across all frequencies, all aspects, and all weather conditions. The question was whether aircraft could remain hidden long enough to complete missions before being effectively engaged. The F-117 represented the first generation of operational stealth. Aircraft proof of concept demonstrating the viability of low observable technology. Its angular, faceted design was dictated by computational limitations of 1970s or computers that could only calculate radar cross-sections. 4 flat surfaces meeting at sharp angles. Later stealth aircraft, including the B-2 bomber and F-22 fighter, incorporated curved surfaces made possible by more powerful computers that could model complex interactions of radar waves with smoothly blended shapes. These achieved even lower radar cross-sections while maintaining far superior aerodynamic performance. The story of the F-117 and Soviet efforts to detect it illustrates a fundamental dynamic of military technology. Every advance in offensive capability spurs development of defensive countermeasures, which in turn drives further offensive innovation. The competition between stealth and counter-stealth continues today. With each side seeking advantages the other will inevitably work to neutralize. For Soviet radar operators who watched their screens in frustration as phantom targets appeared and disappeared, the experience was a humbling reminder that technological superiority is never permanent. The sophisticated air defense network they'd built with such pride had been rendered partially obsolete by a single breakthrough in aircraft design. The phrase "we tracked it for 6 seconds" became a cautionary tale within military circles, a reminder that confidence in existing systems can blind organizations to revolutionary changes. The Soviets had published Ufimtsev's research themselves, never imagining American engineers would recognize its potential. That failure of imagination proved more costly than any amount spent on radar installations. The human element of this story deserves particular attention. Behind technical achievements were individuals who took enormous risks and made extraordinary sacrifices. Pilots who flew the first Have-Blue prototypes knew they were testing aircraft that might prove unflyable. Ground crews who maintained F-117s in absolute secrecy lived double lives, unable to share their work with friends and family. The Soviet radar operators who struggled to track ghost targets were professionals caught in situations beyond their control. They'd been given equipment that couldn't do what they needed, assigned impossible tasks by leaders who didn't understand the threat's nature. Their frustration and confusion was the human cost of technological revolution. The development of stealth technology also represented a triumph of unconventional thinking. The Skunk Works engineers who created the F-117 were willing to abandon assumptions governing conventional aircraft design. They embraced instability, ungainliness, and impracticality in pursuit of a single, overriding goal. Their success came from thinking differently rather than thinking harder. This lesson extends beyond military technology to innovation generally. Breakthrough advances often come not from incremental improvements to existing approaches, but from fundamentally rethinking problems. Ufimtsev's theoretical work was ignored by his own military because it didn't fit their existing paradigm. American engineers succeeded because they considered possibilities that seemed absurd to conventional wisdom. The secrecy surrounding the F-117 program carried important implications. For more than a decade, the aircraft's existence was completely hidden from public view. This required organizational discipline, extraordinarily rare in democratic societies, where information flows freely. The compartmentalization was so complete that even families of F-117 pilots didn't know what their loved ones flew. Wives who noticed husbands leaving for work at night and returning before dawn accepted vague explanations about classified duties. Children grew up unable to understand why fathers couldn't talk about their jobs. This secrecy served its purpose. Soviet intelligence, despite enormous efforts, couldn't obtain detailed information about F-117 capabilities before public revelation. When the aircraft was finally shown to the world in November 1988, it came as genuine surprise to both public and foreign intelligence agencies. The revelation was carefully managed to maximize psychological impact. The angular black aircraft, unlike anything publicly displayed before, seemed to come from the future. Its strange appearance perfectly complemented mysterious capabilities, creating an aura of invincibility that served American strategic interests. In the years since the F-117's retirement in 2008, the full scope of its achievements has become clearer. The aircraft flew in every major American military operation from Panama through Iraq, consistently demonstrating ability to penetrate defended airspace and strike high-value targets. Not a single F-117 was lost to enemy action during its operational career, with one exception that proved the rule. An aircraft shot down over Serbia in 1999 occurred under circumstances highlighting both limitations of stealth technology and adaptability of determined adversaries. Serbian air defenders used unconventional tactics, including visual spotters and adjusted radar frequencies, to detect and engage the aircraft. That loss served as a reminder that stealth isn't a magical shield, but a technical advantage requiring careful employment. The same aircraft that flew through the heaviest defenses in Iraq unscathed was brought down by resourceful enemies who adapted to its capabilities. Technology alone never guarantees success. The legacy of the F-117 extends far beyond direct military contributions. It proved stealth technology was practical, opening doors to development of increasingly sophisticated low-observable aircraft. Every stealth aircraft flying today traces its lineage back to the angular prototype that first flew from the Nevada desert in 1977. The program also demonstrated the value of the Skunk Works approach to advanced development. By giving a small team of talented engineers freedom to work outside conventional bureaucratic constraints, the Air Force obtained revolutionary capability in remarkably short time at relatively modest cost. This model has been cited as an example for innovation in organizations far beyond the military. For radar operators who tried in vain to track ghost targets during the Cold War, the F-117 represented something beyond mere military technology. It demonstrated that the world could change in fundamental ways that rendered existing expertise obsolete. Training that made them elite professionals became inadequate against threats that didn't play by old rules. This experience carries lessons for professionals in every field. Expertise built on current technology and current assumptions can become a liability when conditions change. The ability to recognize paradigm shifts and adapt to them is often more valuable than deep knowledge of existing systems. The story of the F-117 and Soviet attempts to detect it is ultimately about the boundaries of human knowledge and the constant pushing of those boundaries. The same physics that governed radar detection also contained seeds of radar's defeat. The answer was always there, hidden in equations few recognized as practical. Those who succeeded did so because they looked at familiar problems from unfamiliar angles. Literally, in the case of the F-117's faceted design, they questioned assumptions others accepted as fixed laws. They pursued ideas experts dismissed as impossible. The Soviet operators who watched their screens in disbelief were witnesses to historical transition. The world they'd trained for was giving way to a new world they didn't yet understand. Their 6 seconds of confused tracking was a glimpse of that new world, a future where warfare's rules would never be quite the same. Today, principles pioneered by the F-117 have become standard features of military aircraft design. Stealth is no longer revolutionary but routine, incorporated into everything from fighters to bombers to drones. The advantage that once seemed magical has been normalized through decades of development and refinement. But the fundamental lesson remains relevant, somewhere in laboratories and research facilities around the world. Engineers are working on technologies that will make today's cutting-edge systems obsolete. The next paradigm shift is always approaching, even if its exact nature remains unclear. The question isn't whether such shifts will occur, but whether organizations and individuals will recognize them in time to adapt. The Soviets who dismissed Ufimtsev's work failed this test. The Americans who embraced it passed. The stakes were nothing less than strategic superiority in the most consequential military competition of the 20th century. For those who study military history, the F-117 story offers a powerful case study in innovation, secrecy, and strategic surprise. For those interested in technology more broadly, it demonstrates how theoretical insights can be transformed into practical capabilities that reshape entire industries. For everyone else, it remains a compelling tale of ingenuity, courage, and the endless human drive to achieve the impossible. The radar operators who tracked the ghost for 6 seconds never forgot that experience. It challenged their professional identity and forced them to confront limitations of systems they'd trusted completely. Some became advocates for new approaches to air defense. Others quietly retired, unwilling to continue in a profession that had changed beyond recognition. Their story deserves to be remembered not as failure, but as testament to the relentless pace of technological change. They did everything right according to standards of their time. They were undone not by incompetence, but by revolution. They couldn't have anticipated and couldn't have countered with the tools at their disposal. In the end, the F-117 story is about more than aircraft and radar. It's about human capacity for innovation and human vulnerability to surprise. It's about constant tension between the known and unknown, the comfortable and revolutionary. And it's about those moments when the future arrives unexpectedly, changing everything we thought we understood. The black, angular jets that once seemed like visitors from another world have now passed into history, replaced by newer generations of stealth aircraft. But the lessons they taught remain as relevant as ever. In a world of constant change, the greatest danger isn't the threat we can see, but the one we cannot yet imagine. Museums now display F-117s that were once so secret, their existence was denied. Visitors can examine the angular facets and radar-absorbent surfaces that confused Soviet operators for so many years. The aircraft that was once invisible has become an artifact of history, visible to anyone who wishes to see it. But somewhere, in some classified facility, engineers are working on the next ghost. The next technology that will make today's wonders obsolete. The cycle continues as it always has, driven by the endless human quest to see the unseen, to know the unknown, and to achieve what was yesterday considered impossible. The F-117 was not the end of that quest, but one memorable chapter in a story that has no final page. We tracked it for 6 seconds. In those 6 seconds, an era ended and a new age began. The ghost that appeared on Soviet radar screens heralded a transformation in military technology. Its effects are still unfolding today. Those 6 seconds were all the warning the world got that everything had changed. 6 seconds might be all the warning we get next time. The future doesn't announce itself with fanfare. It appears briefly on screens, confusing those who see it before vanishing into the unknown. Only later, looking back, do we recognize those fleeting signals for what they truly were, the first signs of a world transforming before our eyes. So we remember those radar operators, professionals caught between two eras, doing their duty even as the ground shifted beneath them. We remember the engineers who imagined the impossible and made it fly. We remember the pilots who trusted their lives to aircraft that defied conventional wisdom. Most of all, we remember those 6 seconds. That brief moment when the future broke through into the present, when a ghost appeared on screens around the world, and when everything began to change. 6 seconds, that's all they got. But in those 6 seconds, they touched something historic, something that would reshape military aviation for generations to come. The ghost they glimpsed was the future arriving ahead of schedule, invisible to their equipment but unmistakably real. We tracked it for 6 seconds, and those 6 seconds changed everything.